Go ahead, Miguel. What's your question? Or request, rather. Oh, you're talking about music. If I can remember, sure. That's a pretty big if, though. Okay, it's about 3 o'clock here, so let's go ahead and get started. So today's topic is going to be a continuation of PFRs, so plug flow reactors, and we're going to, actually let me stop the music. Okay, that's better. I can hear myself talk. We're going to be going over examples of plug flow reactors, but before we do that, I'm just going to recap some important equations real quick and give you their location in the text. So equation 7.1 is going to be pretty important. This is, of course, the material balance. And the material balance is generally stated as dNi over dV, where V is volume, is equal to the rate law of this of the reaction. And because it's a first order differential equation, we of course need to have a initial condition, which in this case is going to simply be Ni naught at V is equal to 0. The next equation that we're going to need to remember is equation 7.2, which is going to be the energy balance. And this is, of course, dt dV. I'm not really sure I forget what Dr. Drews called this, but I'm going to refer to it as del Q. I think that's the correct term. But that's not, again, it's not it's not a partial derivative or anything like that. It's just del Q. It's heat per unit volume. And then minus the summation of J is equal to 1 Rj delta H divided by the summation of Ni Cpi. And the initial condition for our energy balance is going to be that at volume is equal to 0, T is equal to T naught. Okay, and then one more equation that will be useful in this case is equation 7.19, which is another equation for delta Q, or del Q is equal to UA, that's a little a, times TU minus T. Where A is equal to 4 over D for cylinders. For cylinders only. So if you, for some reason, had an oddly shaped PFR, like a PFR in the shape of a rectangular prism for some reason, your A value would be quite a bit different. So your Q equation would be different. Okay. So in this first example we're going to be going over, we have a PFR, and I will try to draw them, but I am not as practiced at this as Dr. Drews. I always mess it up somehow the first time, and I'm like, I look at it, I'm like, this doesn't look right. I think it's, no, that's something already doesn't look right. Try this one more time. I think that's supposed to be how it's drawn. So a question on these equations, is the V in T, V is equal to 0, equal to T naught, big V or small v? So this is big V. V for volume. And somehow this PFR does not look that as nice as the one that Dr. Drews draws. I should go back to undergrad and learn how to draw these. Make my education worthwhile. Okay, so in our PFR we have, we're given some information. So here we're given that nu naught, that is the volumetric flow rate, is equal to 0.9 meters cubed per second. K is equal to 0.001 meters cubed per mole per second. Na naught is equal to 12 moles per second. And we're given that it is a liquid phase reaction. And it follows an elementary rate law. And the reaction is A plus B goes to C plus D. Okay. Oops. Sorry, I think my page just changed there. Okay, so the reaction is A plus B goes to C plus D. And part A is to find volume for XA is equal to 50%. And so in this case, this first part is relatively straightforward. I think it's similar to an example that Dr. Drews went over on Wednesday, if I'm not mistaken. But if you aren't sure where to start, if we're solving for volume, the material balance is always a really good place to start. And so in this case, the material balance will be written for species A. DNA dV is equal to R sub A. And here we can define the rate law since it's elementary, or instead of R sub A. I always like to define my rate law in terms of the overall reaction, so just R. In this case, because it's elementary, it's simply going to be K CA CB, which is nice and easy. Oh, one more thing I forgot to put in the prompt here. We have equimolar feed. And it's also a couple of things I forgot to put in. Hold on. Yeah, it's isothermal and isobaric. I think that is everything, but I have to double check now. Yeah, that should be everything. Okay. Okay, so from our material balance and our rate law, we know that if we plug in our rate law for RA, which is simply negative R, we can say that the material balance is equal to negative K CA CB, which we then could do a substitution to get that it's equal to negative K divided by nu naught squared times NA times NB. Here, the only substitution I did was that CA is equal to NA over NB, or excuse me, nu, and the same thing for CB as well, NB divided by nu. And we also know that because this is a liquid phase reaction, that nu is approximately equal to nu naught. And so we can simplify it to this equation here. And going a little bit further with the algebra, we can rearrange this equation to, because this is a first order differential equation, we need to, and it's a separable equation, we're going to move some variables around to get all the NAs on one side and all the V's on the other. Fortunately, there is no, the only V we have is this differential V. So times negative K over nu naught squared. And then I'm going to move both of the NAs over to the left side. So we're going to get, sorry, NA and NB. DNA over NA times NB. And the reason in this case why there's a question here. Don't we usually use lowercase v for volumetric flow rate, not nu? I've always been using nu. I've always said nu. So I mean, I think in I think the way that Dr. Drews writes it, he uses v. But in the text, it's at least I'm fairly confident that that Greek letter is considered nu. You're making me question myself now. But yeah, it's you can call it a little v or nu. Another question. We only care about grouping the n terms, and everything else goes with v, right? Oh, okay. Is it really? Huh. Okay, I will try to fix my language and start calling it v then. Okay. Question was, we only group the n terms and everything else goes with v, right? Yes, in this case, because we sort of have a special case here where we can actually, because the equations are, or excuse me, the feed is equimolar, we can say that NA is equal to NB. And so when we rewrite this equation here, we can get DNA over NA squared is equal to negative K V naught squared dV. Yes, you are correct. Nu is for the coefficients of the reaction. So I apologize. The flow rate should be just V. So when I said up here that the when I said nu naught is equal to 0.9, what I meant was the flow rate. So I should have said V naught. And so this here is V, the same V. So this is a flow rate. Um, so the feed is, okay, so the feed is equimolar, which means that, so the question, I have a couple of you asked me, why is the NA equal to NB? NA is equal to NA naught times 1 minus XA. Oh shoot, I actually might have made a mistake here. Did I? Okay. And then NB is equal to NA naught XA, if I'm not mistaken. So I might have made a mistake here. So some of the numbers I have might be wrong, but I'll have to double check. Yes. Okay. Yeah. Thank you. So no, this is correct. So in this case, they're equal because XA is given as 0.5. So 50% of A is converted, which means that because NA and NB are fed in equal molar amounts, XB is also 50%. Thank you for pointing that out. I was freaking out for a second because I thought I had done the math wrong for the rest of the problem, but in this case, NA is equal to NB because of the conversion rate. So in this case, like I said, we can make NA and set NA and NB equal to each other because of the conversion and because of the equimolar feed. And then we just have to calculate the integral now, which is in this case, NA naught to NA and 0 to V for the right side. So calculating this, we get that negative, so the integral here is going to be negative 1 over 1 over x, and then we're evaluating from NA naught to NA. And then this is going on the right side, we're just going to get the volume. If they weren't equal, then would we have just made NB in terms of NA? So yes. Yes, you would write it in terms of NA, and then calculate the integral. So in this case, I made this problem a little bit easier because because NB and NA are related to each other. You can write NB as a function of NA, and you would need to in this case because we're differentiating with respect to NA. We need to lump all the terms with that are a function of NA together and then integrate them together. So yes. And so when we evaluate this integral, we get 1 over NA naught minus 1 over NA. Yeah, so this is, there was a note about, so the question here is X just NA? There was a note about sort of the improper form that we're using, like kind of like a lazy math form that we're using when writing these differential equations. Typically, we would not write both NA as part of the differential and as part of the integral. And so what I'm pointing out here with what X is, I'm just sort of saying that the integral of 1 over x squared generally is negative 1 over x. And so, yes, we could write NA here instead of x, but I wrote x there in my notes just to in case there was any confusion, but apparently it's the x is causing confusion. So yes, x is NA. And so when we evaluate this, we're going to get 1 over NA naught minus 1 over NA is equal to the same stuff on the right over here, V naught squared times the volume. And then rearranging, we can get that the volume is equal to 1 over NA naught minus 1 over NA times V naught squared over K. And given the information that we started with, which was that K is equal to 0.001, V naught is equal to 0.9, NA naught, I think I forgot to give that, but NA naught should have been given as 12. Yes, it was 12. 12 moles a second. Plugging all these numbers in, we get that V is approximately 67.7 meters, which, if you aren't aware, is an enormous size. About a, I mean, so we're all college students, and so you probably know the size of a U-Haul truck. Thank you, M cubed. A U-Haul truck is about 800 feet cubed, which is about 22 meters cubed. So this one reactor is about the size of a 3 U-Haul trucks. Yeah, that's about right. Am I missing a negative? Possibly. Yeah, I think you're right. I think there should be a negative out here. That came from the K term. Okay. So real quick, I'm gonna switch to MATLAB, and I'm gonna show you how this problem could be done using MATLAB. So all this work that I did here, where I actually integrated and then calculated the volume. So this integration and calculation step can basically be skipped using a little bit of MATLAB code. So to sort of save yourself some time on the integration and save the various mistakes that I just made that you all saw, we're going to switch to MATLAB here in a second. Okay, so to save myself some extra mistakes here, I'm going to be copying and pasting at least the majority of this code. So as Dr. Drews pointed out before, the general outline of our code should look something like this, where we call a function and then we need to define a function. And I want to point out one thing that Dr. Drews mentioned and really emphasize this in terms of MATLAB code, because I've had a fair number of students email me, sending me their code and having me look over it. when it comes to writing your code in the first place from the beginning, what Dr. Drew said last class about starting from the end of the code and then working backwards is something I would highly, highly, highly suggest, because not only does it organize your code and keep everything in terms of a set of variables that should be, rather than having magic, what we call magic numbers in coding, everything will be set in variables, which makes reading the code significantly easier, and then debugging the code as a result significantly easier. So our end, if we were to work backwards from here, we'd first want to define our material balance, DNA dV is equal to RA. And then from that, we just need to notice, okay, we have this set of variables that we need to define. So in this case, we need to define RA as R is equal to negative RA. And then we can define another set of variables here. In this case, RA is equal to our rate law. Well, excuse me, this should be, well, no, that's fine. RA is equal to our rate law. And then our various concentration terms are defined. And then ahead of that, we need to define basically all the constants that we have. So in this case, they're going to be our K value, our Na naught value. This is, again, part of the equimolar feed definition. So NB naught is equal to Na naught. Our V naught and it's del H, and this term is part of the next part of the problem. So I'll delete that for now. And then we can define our, outside of the function, we can define our plot. So if I copied this right, this should run. And you should all be able to see my plot on the right here. So we calculated a volume of approximately 67.7 meters cubed. And so if we look at this horizontal line, which is plotted by the function here, yline at 0.5, and we zoom in here, this intersection tells us what roughly the volume that we should be getting at this conversion is going to be. So 67.7 is approximately correct based on this chart. It's actually a little bit higher. It's like 67.8 something. But anyways, so yeah, we should get a, this is the kind of code that you would use to solve material, just a straight material balance. And I will be posting this code along with the lecture after class today. Okay, so let me switch back to the screen over here. Okay, so that problem was pretty straightforward. So the next part is will take a little bit more work. I think the material balance generally is a little bit easier than the energy balance. But so this next part is given delta H is equal to negative 540 kilojoules per mole. Find Tu for isothermal operation. Okay, and so we're going to go back to our energy balance, which is equation 7.2, which will, in this case, simplify quite a bit because we are operating isothermally. And in this case, what that means is that the entire left side of the equation is going to cancel out. Oh, wait. I think I have, I'll copy this. This is the more general form. So this is equation 7.2. This is the energy balance. But because we are operating isothermally, this whole term on the left will cancel out. And then this term on the bottom, we can move over to the left and cancel out as well. So we can basically simplify that down to 1. And our final equation in this case simply becomes del Q is equal to this summation here, keep in mind, is for the summation of the rate laws over all reactions. Because we only have one reaction, this summation basically goes away, and now it's just RA, excuse me, not RA, R delta H. Because it's not over the species, it's over the reaction number. So this would, if we were to put a subscript on it, it would be R1 for our one and only reaction in this case. And so doing the substitution for R here, we can get that del Q is equal to, the chat window disappeared again. Okay, so del Q is equal to generally just KCA CB delta H. But we also know that CA is equal to NA over V. In this case, which is also equal to V naught because we're in liquid phase. And so we can say that this can simplify down to similar to what we did before. This is going to become NA squared delta H. And here we can make another substitution for NA such that we get things in terms of the conversion that we had, which is going to give us NA naught times 1 minus 0.5. So making that substitution, we get that K over V naught squared times NA naught times 1 minus 0.5 times delta H is all equal to del Q. And so from here, if we substitute in our numbers, sorry, you're right, there's a square here. Del Q is equal to U times, actually, we'll use that equation in a second here. If we substitute in our numbers, in this case, we should get that K is equal to, someone might want to check my math on this because I did change numbers around quite a few times. So K was equal to 0.001, V naught was equal to 0.9, NA naught is equal to 12, and del H is equal to negative 540. 540. So del Q should be equal to negative 24 kilojoules. Now we also know that we're looking for del Q for isothermal, excuse me, we're looking for TU for isothermal operation. So now that we have del Q, we can find TU, which is going to be equal to del Q is equal to UA times TU minus T, where T is the reactor temperature, which I don't think I specified, but it should be 400 K. Yeah, isothermal operation at 400 K. So question, NA is equal to NB no matter the conversion rate because they're 1-to-1. Yes, I believe that should be true. So dq here, or del q, is going to equal to, now I didn't specify a value for u, and the reason is because we're going to be calculating u in two instances. So I'm setting up this example in a sense to sort of show you the different options that you would have in sort of a real world design problem. And so let's say that the amount of energy you need to remove from the system, in this case, is negative 24 kilojoules. And we have two, I'm going to give you two options in order to remove the heat. So you're going to remove it through a heat exchanger, but you can either use water, where U is equal to 600 watts per meter squared K. So this would be water. Or you could use air. And let's say that you were just cheap and you didn't want to purchase huge sums of water in order, because if you think about what we're trying to cool here, we're trying to cool 3 U-Haul trucks worth of fluid. The amount of water that you would need to cool that would not be, I mean, it could be fairly significant in terms of just the weight and the amount of the container, the reservoir to hold that amount of water that you would need. So it could get fairly expensive, but you could also potentially use air. So in the case of air, we would be looking at a U value of 56.6 watts per meter squared K. And so we're going to calculate the value for TU in both of these circumstances and sort of look at the different dimensions that we can potentially have. So in this case, if we had a diameter, again, this is assuming our PFR is a normal cylinder shape, not some otherwise unusual shape. Diameter is going to be 0.1 meters. And then we'll also do it if we had sort of like a giant pipe of 0.5 meters. So half a meter is probably a little bit over shoulder width. So like Dr. Drew said on Wednesday, you can easily fit somebody inside a 0.5 meter pipe. And whereas 10 centimeters is roughly probably the diameter of your face. When we are looking at the diameter, in order to calculate the length, if we look back at our equation for volume, we knew that volume is 67.7 meters. And the volume of a cylinder in this case is going to give us pi over 4 d squared times L. And so given these diameters, you can use that equation to find that the length in the case of a 0.1 meter diameter is going to be a rather obscene length. It's 8,600, about 8,600 meters, 0.8 meters. This is roughly the equivalent of 78 football fields in length. And so you realistically, if you were designing this, technically you could probably, if you had a football field, which if you didn't know is approximately 50 meters in width and about 110 meters, I want to say 110 meters in length, you could theoretically actually zigzag this thing across the football field 86 times, and in order to fit it within a football field. But this is, practically speaking, this is not something that you would typically do. But if you did do this, using the equation, or rather rearranging this equation so that we can write this as to solve for TU, we get an equation that looks like T plus del Q over UA. And then this is, in this case, using the numbers that we have, we're going to put 400 plus del Q is, or negative 24,000 times the diameter divided by U times 4. And so if we were to do the calculation for the TU of in our system of when we use water, we'd actually get 399K. And so the amount of, keep in mind that when we have del Q of negative, that means our reaction is exothermic, so it's releasing energy. And that's the amount of energy we'd have to remove from the system to compensate for the exothermic reaction. And because our reactor is running at 400K in this instance, the water that we need to cool down the system is almost 400K. What that means is essentially if we're using water as our cooling agent, we basically don't need, we don't really need to cool it that much because it's already being cooled essentially by water that's almost at the same exact temperature. And then if we were to use air though, we would get 389.4K. And so even here, in this case, using air, we could cool the system reasonably well. It's negative 24 kilojoules. It's not 0.24 kilojoules. So, oops, I did not mean to put a decimal. It's negative 24. And so if we were to use the same system, but we're using air in this case, then we get that the air only needs to be at a temperature of about 389. So still roughly the temperature of the reactor. It doesn't need to be significantly colder to remove that amount of energy. This is, keep in mind when we're calculating these temperatures, if we were to go, say if we were to run the system cooler, then we'd be cooling the system too much. If we run it hotter, then it's not enough to remove the amount of energy and the system could overheat. Now, if we were to move up to a 0.5 meter diameter, which is fairly large diameter as far as these pipes are concerned, but it'll reduce our length significantly down to 344.79 meters in length. How do you do the calculation for L? So you would use this equation up here. And you could rearrange that equation for L. So in this case, it would be 4 divided by pi divided by diameter squared is equal to L. Okay, and then so in the same system, if we were to use water, but we're using a larger diameter now, this slightly changes the temperature of our water, but not by much. We would still need water at 395K. And so in this case, in the case of air though, what ends up happening is that we end up needing air to be 346.99K, so about 347 degrees K. If we think of that in terms of 347, in terms of degrees Celsius, we're looking at about 74 degrees Celsius, which is still fairly warm. I actually don't know what that would be in Fahrenheit, but in any case, 74 degrees C is still pretty warm air. But as opposed to say heating water up until 395K, which is roughly 80 or 90 degrees C, it might be more worthwhile to just heat up air, especially if you're in a hot environment and you could just pump air from the outside and then warm it up a couple degrees. You'd potentially end up saving quite a bit of money. But of course, that also depends on the specific heat of air versus water and how much energy input you would actually need for that. But this kind of thing would sort of affect your consideration in terms of the design process of your PFR. Now, realistically, I think that, I mean, a 0.5 meter diameter is already pretty huge. And then to say that a 0.5 meter diameter runs the length of the equivalent of 3 football fields, this reaction is already somewhat absurd. But I don't know, maybe there's some reactions that do that. I don't know. In any case, the choice, you can tell by these numbers that the choice of your fluid in your heat exchangers can make quite a bit of difference, and potentially change the cost of your system, depending on how much you're trying to heat your fluid in the heat exchanger and how much of it you need. Algae ponds are about that big. Okay. Actually, yeah, that's about right. There's algae ponds in Hawaii that are if you look at pictures of it, you can see that they're massive massive tanks. Okay. So there was one more thing I wanted to show you, which was MATLAB code for this portion of the problem, the energy balance problem. But I actually couldn't get the code to work before class, so I will, as soon as I get it working, I will post it up on Canvas alongside the other code. But I think, yeah, that's all I have for you today. As always, I'll be hanging out for any extra questions. If I might have missed a question or two as I was going through, so I apologize for that. But feel free to send it to me again if you had any questions. So question was, what are some other utilities that are commonly used? So I want to say water is probably the most common. Water, air, and steam. In the case of, like, if you needed to heat something up as opposed to cool it, you could easily use steam in such a case. If you look in table 4. I think it's 4.1, 4.2. That shows the different U values for, or rather different H values for different substances. Those are the most commonly used utilities in heat exchangers. So takeaway today is the choice of utility material depends on diameter of the pipe. It's affected by the diameter of the pipe. Oh yeah, fire. That makes sense. That's probably a very common utility for heating things. Takeaway today is the choice of utility material depends on the diameter of the pipe. It certainly is affected by the diameter of the pipe and the geometry of your system. But really, I think the choice of utility will come down more to likely to cost and practical implementations, more so than the exact temperature that you need. But the diameter of the pipe does affect the temperature of the system, or the temperature of the utility that you would want to use. So in this case, both water and air at these temperatures for the 0.5 meter pipe, you're looking at, in Fahrenheit, you're looking at between 176 degrees Fahrenheit and about 250, if I'm not mistaken, degrees Fahrenheit for the water. So I mean, in both instances, you're looking at, you're going to have to heat whatever fluid you use up quite a bit from like room temperature. And so which one you use would probably come more down to cost and implementation. I'm gonna just put some music back on so I don't feel so uncomfortable. Okay. Sounds good, Dr. Drews. Thank you. I think it's good that we can end it here. There's only about 4 of us left. I'll email you about the about next week. You too.